Okay, these titration curves are on the handout you just picked up when you walked in. So this is a quick little review from yesterday, and then we'll work a few problems. On that first curve right there, what I want to know from you, first off, is what type of titration is this? We talked about strong, strong, or weak, strong. Which one do you think this is? Weak, strong. Can anyone tell me why they think that? Hannah? There's a buffering region. I'll give you that. There's actually going to be an easier way to distinguish where you can look at 1 point. Nimish? Okay, less extreme start. This is questionable though because that's still pretty extreme, so that would be an iffy one, Nikita. The equivalence point pH is not at 7. That's going to be your quickest indicator. So if you look, whereabouts is the equivalence point here? Like somewhere in there, right? So that's telling us we're not a strong, strong situation. What that is telling us, though, is what is strong in this titration and what is weak. Is the acid strong or the base strong? So this is a strong base and a weak acid. Now, something else I want you to be able to tell me is what's in our beaker in the titration and what's in the burette. Meaning, in the burette, we're adding stuff. So what would be the units down here? Mils of base. Why is it mils of base? Right, we're starting acidic and we're getting more and more basic the more we add. Okay, so therefore that means the acid is in the beaker. All right, let's do the same thing for the next one. Evaluate it. So what do you think? Yeah, this is definitely a strong, strong. We have an equivalence point of 7, okay? Super steep, sharp rise there. So this is strong, strong. The only thing left to tell me is what's the titrant, acid or base? Again, base because we're starting at an acidic pH, and adding base brings us to eventually a basic pH. Okay, and making sure this is blinking. Yes. Okay, let's go to the next one. So that's definitely kind of ugly. When they're ugly, they're going to be weak, strong. Where's our equivalence point? About 5. So what does that tell you about what's strong and what's weak? What's strong? The acid is what's strong. The base is what's weak. And can you tell me what we're adding? This time we're adding acid. That's in our burette, and the base is in the beaker because we're starting out with a high pH. Very ugly graph, but very typical of what a weak, strong titration curve looks like. Okay, so now let's move on to the next part of the sheet. I want to talk a little bit about indicators. Every single one of you, regardless of what level of chem you took at Westlake, did a titration. Okay, and you used drops of an indicator. What indicator did y'all use? I know you all used the same indicator. Louder, Jillian? Don't read it. Say it as you've heard it. Phenolphthalein. If you try to read it, you're trying to sound out a word that looks absolutely nothing like it's spelled or sounds, whatever. Anyway, it's phenolphthalein. And indicators, what's cool about them is they themselves are acids and bases, which are weak, or usually they're weak acids, but they can be weak bases as well. But they change color at their pKa. So what's really cool about them is we can, knowing when they change color, we can pick an appropriate indicator for whatever titration we're doing. Phenolphthalein, this is the colorless form. And then the pink form is missing an H. They're just, Laurie Brown said, they're conjugate acids and bases of each other. Notice here I say they change color at their pKa, meaning the negative log of their Ka, plus or minus 1. What's up with that? Well, there's a range, okay? Our human eye cannot see exactly the moment it changes color. We see clear to a lighter pink to a dark, you know, that kind of thing. You see a range. And that range ends up being plus or minus 1. I'm going to show you how it works using Henderson-Hasselbalch. You don't need to know it to ever repeat it, but I think it's just cool to know. The Ka for phenolphthalein is 1 times 10 to the negative 9th. If that's the Ka, can you tell me what the range of color change is for phenolphthalein? When does it change exactly? You're getting out your calculators, you people that are in like pre-cal, advanced calculus, multivariable, whatever. What the heck? What's the negative log of that? 9. Okay. So this changes color at exactly 9. What's the range? 8 to 10. Okay. So we're going to use this on titrations that what is between 8 and 10? What are we looking for when we're titrating? Not the equilibrium point, equivalence point. So we want a titration where the equivalence point falls between 8 and 10. Okay. Looking at, this is the pink form. It's missing up here. There was an H on the colorless form. That's the pink form of phenolphthalein. But how it works is, let me explain the whole plus or minus 1 thing. So this is an example of a different indicator called bromothymol blue. It starts out yellow and turns to blue. It's yellow in acid and blue in base. So, or actually that's reversed. It's actually blue in acid, whatever. So anyway, the K is 1 times 10 to the negative 7th of this. So its endpoint is at 7. So the question is, well, why do we need plus or minus 1? Well, the human eye can only detect color change if 1/10, at least 1/10 of the yellow has become blue. Any less than that, we can't see it. Okay? And vice versa, if we're going the other direction, 1/10 of the blue becomes yellow. Once we hit that 1/10, we can actually see it. So that's going to create, and this is really cool, if you look at Henderson-Hasselbalch, remember, these are conjugates, right? We're dealing in a normal acid-base system, conjugate acid-base system. So if you're saying, in order to see color change, I need at least 1 of these to every 10 of those, you get your endpoint of 7, and then the log of 10 over 1 is 1, so we get 8. That's one end. And then the other end, whoa, did I skip one? There it is. And here, if we're going the other direction, we need at least 1 of these to every 10 of these to start to see things. And when you do that, you get a -1, so you get a 6 on that end. So it's a 6 to 8 range. I think that's really kind of sexy. All right, so that's why you'll never have to repeat this. I just thought it was interesting. What you do need to know is that an indicator changes color at the pKa plus or minus 1. That's the range. So one little thing that might be an issue is choosing indicators that work. And it gets confusing, but you have to be able to decide what indicators are best for what titrations. You do not obviously need to memorize this. This is just showing you different indicators that exist and what pHs their ranges are at, their color change is occurring. So here's an example. What kind of titration is this? Strong, strong. Now, you guys did strong, strong titrations in pre-AP in last year in Chem 1. You used phenolphthalein. When is strong, strong changing color? I mean, not color. When does strong, strong equivalence point? 7. We said the range of phenolphthalein was 8 to 10. How come it is okay to use phenolphthalein on a strong, strong? Yeah. No, it's not a small difference between 7 to 8. What are we doing? We're adding drops of base, right? Okay. So if we're here, okay, so this is 8 to 10, and this is the equivalence point. Is there a significant difference in the amount of NaOH we would add here to there? No, that might not even be a drop. Because of that sharp rise, the volume is not any different. And basically, 1 drop covers that entire pH range because of the sharp rise. So it's okay to use phenolphthalein. Methyl red, it looks like it's really hard to see. I think it's like 5 to 6, somewhere in there. That's methyl red's range. So is it okay to use methyl red on this titration? Yeah, right? Is this a change in volume from here to here of added on that steep rise? No. So we're safe using either methyl red or phenolphthalein on a strong, strong. Okay? There was something else I was going to tell you, and it escapes me right now. Oh, I know what it was. Equivalence point is what? Again, repeat. When, correct. There's a term that you're going to hear a lot, and a lot of teachers and a lot of people I hear talking get them confused. There's something called endpoint. The endpoint is when the indicator changes color. The equivalence point is when the moles are equal. So the endpoint is when the indicator changes. A perfect scenario is having an equivalence point close to the endpoint. Don't get this confused. This is not an endpoint, it's an equivalence point. Okay, anywho, let's look at the next situation. Here we have sodium hydroxide as our titrant. What's our acid, strong or weak? This is a weak acid. Okay. Are either one of those indicators acceptable for this? We say that phenolphthalene's 8 to 10, and this guy is like 4 to 6. Can I use both of them? No. Who are we going to use? We're going to use phenolphthaleine. That's an acceptable one because the actual equivalence point falls within the range, so we're good. Where it's not so good is here. This is a visibly different volume. Like, that's measurable. Like, that's mils of a difference from this to here. Does that kind of make sense? That's mils added in order to get there. So that methyl red would not be a good choice. So let's apply this. I'm going to try to pull the other, get your other handout out. Your in-class problems. And we're going to solve this problem. Because of my amount of space, I probably won't be doing too much writing here. You're going to have to take your own notes. But I'll write down as much as I can. So here we have a titration curve. It says a 30 ml sample of a weak monoprotic acid. What does it mean, monoprotic? 1H. So that's a curve for monoprotic acid. I'm just curious, what would a curve for like a diprotic acid look like? How do ions dissociate from acids? Step by step, right? Does anyone want to guess what a titration curve for a diprotic acid would look like? I'm seeing people do it. You're doing 2 steps, meaning 2 equivalence points, exactly. So if we had a diprotic acid, we'd have a curve with 2 equivalence points. If we had a triprotic, the last one would be barely visible, but we would have a triple, 3 equivalence points, okay? That's coughing, and I'm not sick coughing. Just saying. Okay. Anywho, we're taking this monoprotic acid, and we're titrating with a standardized solution of NaOH. What does it mean that a solution is standardized? It's not the same molarity. All solutions are only 1 molarity. It means we know the molarity. Okay? We know the molarity here. That's what that means. A pH meter was used to measure the pH after each increment of sodium hydroxide, and then the curve above was constructed. Explain how this curve could be used to determine the molarity of the acid. All right, this is how we did that first lab. How do you find the molarity of the acid? We know we use 30 mils of it. We don't know its molarity. But we know a lot about the base. That base is the known. What was the first step in titrations? What do we look at on the curve, guys? This is not new information. The equivalence point. What part of the equivalence point do we care about? The milliliters it took. How many mils did it take to get this equivalence point? Just ballpark it. So we're going to take the mils or liters of NaOH, and we're not going to do calcs because it's not asking us. It's saying explain how to do it. We're going to take the mils or liters of NaOH and do what? We already have it. We did the titration. Stoic. Multiply by the molarity to get what? And this is moles of base. So why do we do that? What by definition is the equivalence point? Yes, when moles of OH equal moles of H plus. So what do we now know? Moles of H plus. It's asking us to find molarity of acid. If I know the molarity, moles of acid, how am I to get the molarity? Which I actually have a number, which is what? Right here. 0.03 liters. And that will give us the molarity of the acid. If you didn't remember that at all, you need to do your homework, okay? Because I know some of those are in the homework. Explain how this curve could be used to determine the Ka of the weak monoprotic acid. Not at the equivalence point. So we want to find the midway point or the halfway point, and right now the equivalence point we said was like 24 or something. So where would the midpoint be? At what mils? 12. What's true about the halfway or the midpoint? What's that statement? Okay. So the pH is 5-ish. So without calculators, what would the Ka be? Yep. 1 times 10 to the negative 5 would be the approximate Ka of this acid. And remember, this is true because half of this acid was turned into A-, so we end up with the same concentrations of HA and A-, and in Henderson-Hasselbalch, those cancel out, so pH is equal to pKa. If you're going to repeat the titration using an indicator in part C, which one would you choose and why? Which one's going to be good? When does an indicator change color? At its what? At its endpoint, which is what? Not its Ka, it's pKa. We change at pHs, so it's pKa. So which is going to be your best option? Crescel red is changing at a pH of 8, so that's like a 7 to 9 range. So that's going to be the best option based on where the equivalence point is. And finally, sketch the titration curve that would result if the weak monoprotic acid were replaced by a strong monoprotic acid of the same molarity. I'm just going to draw on top of the curve. How would it be different and how would it be the same? Start lower, okay. And where would the equivalence point be? 7. So I'm going to go pretty low until here, and I'm going to jump up. And my equivalence point is going to be right there. And I'm going to end very similarly because it's the same base. So once that acid gets overwhelmed, it's the same base that takes over. So we're going to make sure that we have equivalence point at 7, and we start out lower and come up. Okay, that's that problem. Now let's do a little math review problem, the next one. You'll need calculators for this bad boy. A sample of 40 mils of acetic acid is titrated with 0.150 molar OH minus. Forget the word titrated, just go back to classifying over here. What kind of problem is that? It's an invader. We need an invasion equation. And that's the key. A lot of people will look at this in the first part A, says, what volume would you need to reach the equivalence point? People start freaking out because they don't know, what do you mean? How do I do that? Go back to the basics. Go back and write your invasion equation. So what are we adding? We're adding OH minus to acetic acid. And we're going to have an invasion, and we're going to make that plus water, the acetate plus water. The sample, let's just write down what we know about this. We know that we have 40 mils of a 0.1 molar of this, and we know that this is 0.150 molar. So A is asking, what volume do we need to reach the equivalence point? Well, what's the first thing I know from looking at the given information? Moles of acetic acid. So 0.1 times 0.04 is 0.004 moles. So to be at the equivalence point, I need 0.004 moles here as well, right? Well, I know the molarity is 0.150. Molarity is moles over liters. So how many liters do I need to do this? Say it again. 0.026 liters, which is the same as 26 milliliters. Okay, so that's the answer to A. B says, what molar concentration of acetate is at the equivalence point? They're asking you to do the invasion. You already know how to do the invasion. We'll just finish it. So we originally have 0. How much do we lose? 0.004 minus 0.004. Here we go. That's how many moles of the acetate we have after the invasion. Are they asking for moles of acetate? No, they want concentration of this acetate. So what do I divide that by? Total volume of 66 mils, or 0.066 liters. So what's my concentration of acetate? 0.061. All right. That's done with part B. That's B. Okay, how do I do part C? What is part C asking? What's the pH at the equivalence point? So they could have just asked, what's the pH of the equivalence point, and you would have had to have done all these steps. They're being really nice by taking you part by part through that process. So part C now, we need to know what the pH is. After the war, what kind of problem do we have? This is a hydrolysis problem. So what do? Add water. There it goes being crazy again. Looks like I'm got Tourette's of the hand. Whatever. Okay, so go ahead and add water. Maybe it'll stop acting up in a second here. So we're going to do a rice table. Oh, come on. Acetate plus water gives us acetic acid plus OH minus. People at home think I can't draw. It's not me, it's the board. So our original concentration is 0.061. We're going to lose X, gain X, gain X. X is negligible. We have a problem though. What's our problem? Correct, we need a KB and we only have a KA. So we're going to take 1 times 10 to the negative 14th, and we're going to divide it by the KA of 1.8 times 10 to the negative 5th, which is found in the problem right there. Set that equal to X squared over 0.06, 0.061 actually. So what y'all get for X, which is equal to the OH minus concentration? .82 times 10 to the negative 6. When we take the negative log of that, we're calculating POH. What'd you get for that? giving us a pH of 'All right, so those are our review problems. You guys have got to start doing your homework because this stuff, we're through the most difficult stuff. Tomorrow we're doing KSP, which is not too hard, but it's kind of different. So you really need to get this hammered down. So let's clear off our desks. We're about to start our quizzle